In 2025, China strapped a 1-ton sled onto a magnetic test track and accelerated it to 700 kilometers per hour in 2 seconds. That is faster than a fighter jet at takeoff, done on a ground vehicle, with no fuel, no wheels, no engine. And yet, right now, there are exactly 7 operational Maglev trains in the entire world. 7. Across every country, every city, every continent. This is a technology that has been called the future of transportation since 1970. That has broken speed records no wheeled vehicle will ever touch. That eliminates friction, reduces maintenance, and moves people faster than anything else on the ground. And it has almost completely failed to exist. In the next 12 minutes, you are going to find out why. The physics problem that nearly no one talks about. The $1.3 billion train in Germany that was abandoned and left to rust inside a facility built specifically for it. The political decision that killed Maglev in the country that invented it. And the one scenario where Maglev might actually win if it doesn't get killed again first. There is one thing that every government that has ever tried to build a Maglev line has discovered: always too late. We will get to that at the end. But first, you need to understand what Maglev actually is, because most people have the wrong picture in their head. The idea is simple. If you can lift a train off its track using magnets, you remove friction entirely. No wheels grinding on rails, no physical contact at all. The train floats, and when there is no friction, the only thing limiting speed is air resistance, which means the theoretical ceiling for a Maglev train is not 300 kilometers per hour. It is not 500. It is whatever speed the aerodynamics and the power supply allow. The first working Maglev demonstration happened in 1984. Birmingham, England. A short elevated track connecting an airport terminal to a railway station, 600 meters long. Top speed, 42 kilometers per hour. It closed 11 years later. Reliability problems. That gap between what Maglev promised and what Maglev delivered has defined the technology ever since. Now, there are 2 completely different ways to build a Maglev system, and understanding the difference explains almost everything about why this technology has struggled. The first method is called electromagnetic suspension. This is the system used in the German Transrapid, which became the Shanghai Maglev, and in most early commercial designs. Here is how it works. Magnets on the underside of the train are attracted upward toward a steel rail above them. That attractive force lifts the train. Simple in concept. But the gap between the magnet and the rail, the distance that keeps the train floating, is less than 1 centimeter. Less than 1 centimeter. Maintained at hundreds of kilometers per hour, across dozens of kilometers of track. If that gap gets too large, even slightly, the magnetic force drops and the train begins to fall. If it gets too small, the force spikes and the train is yanked upward into the rail. To prevent either, the system measures and corrects its own position thousands of times every second, automatically, continuously, without a single failure. At low speeds, this works. At high speeds, every tiny imperfection in the track, every fluctuation in the magnetic field, every change in temperature or wind becomes a potential instability. Passengers on the Shanghai Maglev have reported for years that the ride is not as smooth as expected. Not rough, but not the silent, floating experience the brochures promised. So engineers reduced the speed. The Shanghai Maglev is capable of over 430 kilometers per hour. In daily operation, it typically runs at around 300, below its own design limit, because the stability problem at full speed has never been fully solved. The second method is completely different. This is what Japan uses: superconducting magnetic levitation. Instead of attracting magnets, Japan repels them. Superconducting coils on the train, cooled to minus 269 degrees Celsius, generate a magnetic field so powerful that it induces opposing currents in coils along the guideway. Like poles facing like poles, the train is pushed upward, not pulled. And because superconducting magnets have zero electrical resistance, the system is far more stable and far more powerful than electromagnetic suspension. The result, Japan's L0 series, set the world land speed record for a rail vehicle, 603 kilometers per hour, on a test track in 2015, a record that still stands today. So Japan solved the stability problem. Why is Maglev still not everywhere? Because solving physics was never the real problem. The real problem has 3 parts, and each one is harder than the last. Part 1. The infrastructure trap. A Maglev train cannot run on any existing track in the world, not one. It needs a completely new guideway, built to tolerances far tighter than conventional rail, with integrated electromagnetic coils along every meter of the route. You cannot upgrade an existing line. You cannot run a Maglev on an existing rail for part of a journey and switch systems. You start from zero. Every time. The cost of building a Maglev guideway is estimated at between $50 and $120 million per kilometer. For comparison, conventional high-speed rail costs roughly $20 to $40 million per kilometer to build. And conventional trains, once built, can run on hundreds of thousands of kilometers of existing track that are already paid for. This is not a cost problem. This is a mathematics problem. Every country in the world has already invested billions in conventional rail. Building Maglev means writing off everything, every station, every maintenance depot, every control system, and starting again, from scratch, everywhere. Part 2. Germany had it, and threw it away. In the 1970s, West Germany began developing the Transrapid, an electromagnetic suspension Maglev system. By the 1980s, it was running on a dedicated 31-kilometer test track in Emsland, reaching speeds above 400 kilometers per hour. The German government was considering a full route between Hamburg and Berlin, 292 kilometers. A showcase for German engineering, a demonstration to the world. The cost estimate was 8.9 billion Deutschmarks. By the time the political debate was finished, it had risen to 17 billion. Then questions emerged about who would pay. So the federal government said it was a private project. Private investors said they needed government guarantees. The circular argument lasted years. In 2000, Germany canceled the Hamburg-Berlin route entirely. 2 years later, China opened a Transrapid line in Shanghai, built with German technology, operated by a Chinese company, connecting Pudong Airport to the edge of the city. The country that invented the technology canceled it. The country that bought the technology built it. And then Germany, watching China operate German Maglev, shut down its own Emsland test facility in 2011. The trains are still there, sitting inside a building, going nowhere. Part 3, and this is the one nobody wants to say out loud. High-speed rail got better, much better, faster than anyone expected in the 1970s, when Maglev seemed necessary. China's conventional high-speed rail network now carries trains at 350 kilometers per hour, commercially, daily, on 40,000 kilometers of track. France's TGV network connects dozens of cities. Japan's Shinkansen has run for 60 years without a single passenger fatality from an accident. For most routes, the speed difference between high-speed rail and Maglev is real, but smaller than it sounds. Tokyo to Osaka takes 2 hours and 30 minutes on the Shinkansen. A Maglev would do it in 67 minutes. That 1 hour and 23 minutes of difference costs, at current estimates, roughly $82 billion to build. Just for that one route. Governments looked at that equation and chose the cheaper answer. Every time. So where does that leave us in 2026? China accelerated a 1-ton sled to 700 kilometers per hour in 2 seconds in 2025. They also tested a separate prototype at 650 kilometers per hour on a dedicated high-speed track in Hubei province. They have the CRRC 600, a full-size passenger maglev capable of 600 kilometers per hour, sitting in a facility in Qingdao. And they have the world's largest high-speed rail network, which they built in 20 years, to prove they can deliver large infrastructure at scale when they decide to. Japan is still building the Chuo Shinkansen, delayed to 2035 at the earliest, cost now above $82 billion. 90% of the route is in tunnels, the most expensive railway project in human history, and it is a maglev. And now, here is the thing that every government that has tried to build maglev has discovered. The thing I mentioned at the beginning. By the time you finish building it, the world has moved on. Germany canceled its maglev line in 2000. By 2008, China had built 6,000 kilometers of high-speed rail. By 2025, China had 40,000. The window where maglev had a clear speed advantage over conventional rail, that window was open for about 15 years. And during those 15 years, no major maglev network was built. Japan's Chuo Shinkansen was approved in 2011. It will open in 2035 at the earliest. By 2035, China may be running passenger maglevs commercially. The technology Japan spent 60 years developing may face a Chinese competitor before it even opens. Maglev did not fail because the physics were wrong. The physics work. The record books prove it. 603 kilometers per hour. 700 kilometers per hour for a sled. Potentially 1,000 within a decade. Maglev failed because the economics were wrong, because the politics were wrong, because the timing was wrong, because the world built something cheaper and good enough and called it done. The technology that was supposed to make trains fly is real. It has always been real. The question was never whether maglev could go fast enough. The question was whether anyone would ever be willing to pay for it. So here is what we know. 7 operational maglev trains in the world, 1 in Japan, 4 in China, 2 in South Korea, none in Europe, none in North America, none in the Middle East, none in Africa, none anywhere that a conventional train could not have done the job for a fraction of the cost. But China tested 700 kilometers per hour in 2025, and China has proven it builds infrastructure faster than any country in history when it decides to. The question is not whether China can build a maglev network. The question is whether China will decide to, or whether, like everyone before it, it will look at the numbers and choose conventional rail again. We are covering China's full maglev plan and what it means for Japan's $82 billion bet. Hit subscribe so you don't miss it. And drop in the comments. Do you think maglev will ever be built at scale? Or is high-speed rail always going to be good enough? I will see you in the next one.